Okay, we have started the recording and I will start this backup recording also. Okay, now we are all set. Okay, so in the previous class on Monday, we had started our discussion on this on to define displacement. As you can see here, we did various things, and ultimately we arrived after this Taylor's expansion at this particular form of the when we were considering these 2 points, we obtained the in the new configuration or in the elemental line segment vector associated with that, the matrix representation of that we arrived at in this form. Now, all this is fine, but the point where we left off on Monday was with me mentioning that it is all right to look at these kinds of vectorial representations or the equivalent matrix representations, but in terms of actual measurements, it is far more useful to look at the actual lengths. Instead of the vectorial representation, it is far more useful to actually get an idea of the lengths. Now, if we compare the length in the deformed configuration of this elemental line segment dx vector with the length in the original configuration, that is the undeformed configuration, d capital X vector, then we have to deal with these kinds of square roots. Okay, so this was our rough column. We saw that this was our thing. Now, it is not very convenient to work with these square roots, which is why I mentioned that without losing any information, we can equivalently think of trying to compare not directly the absolute values of this, rather the squares of these absolute values. If our idea is to compare, we might as well do this kind of a comparison between the squares. The benefit here immediately follows from the fact that the moment you want to work with these kinds of squares, dx vector magnitude square, you understand that dx vector magnitude square is easily representable in terms of the dot product of the vector with itself. Similarly, the d capital X vector magnitude square, that is equal to the dx vector dotted with itself. And we are very much comfortable working with these kinds of dot products. That is the idea going forward. Now, all this is fine. I mean, these kinds of algebraic manipulations, clever tricks, all that is fine. But we must take a step back and ask ourselves, what for are we doing all these things? Okay, because let us not lose sight of the fact that we want to arrive at a point where we will be able to write down some expressions for the strain transformations, meaning that we are working with the strains in a particular coordinate system. If we change or if we rotate our coordinate system, what will be the values of the strains there? So how does all of these things help? And for that, I will definitely show you the steps and all the details. But before going forward, let us have a clear picture in terms of an analogy with what we did earlier. So in the previous topic on the transformation of stress, okay, previous topic of transformation of stress, we first of all tried to find out this sigma nn or the TNN. So basically we found out the component of the traction vector along the normal to a particular plane, and then we went on to find out this sigma ns or the TNS. This was our overall structure of presentation. Here also, in this topic of transformation of strain, our idea is similar. We are talking about these deformations in terms of this general vector dx, d small x vector, d capital X vector, but we want to determine the uh, the nature of the deformation along a particular given direction. This is what we want. So suppose we have a given direction, a direction given by the unit vector n. We want to find out what the strain is along that direction, because if we are able to do that, then in a very general way, then we might as well be able to obtain these rotated versions, like going through theta and then obtaining the expressions. So we'll see what I'm talking about. So first of all, what we'll say is that we'll go back to the easiest definition of strain, which you are all familiar with. So what is that definition? Definition is simple, that strain is defined to be the change in length divided by the original length. Okay, you don't even have to go to your first year. You can, you can go back to your high school physics for that understanding. So what we'll say is that the strain, generally the strain that is defined, again I'm using the symbol for the definition, just like I had used it earlier for the case of the definition of the displacement vector. I'm saying that the strain is defined like this. So please take a close look at what I have just written. The strain is equal to the absolute value of the vector in the deformed configuration minus the absolute value of the vector in the undeformed configuration divided by the absolute value of the vector in the undeformed configuration. So this is the change in length in the numerator, and in the denominator. So it is written in terms of this elemental vectors and very sophisticated way, but ultimately it is just like increment in length divided by original length, or change in length divided by original length. That's all there is to it. Now with this very simple kind of understanding or simple kind of definition, we can proceed forward and get some very sophisticated expressions. Let us try to do that. And the following steps that I'm going to do, that has nothing to do with specifically two-dimensional or three-dimensional. It's a very general kind of thing. Okay, so what we'll do is we'll first start out with this d small x vector. Let me go to the new page. So we'll start with this d small x vector, absolute value of that, and the square of that. So this is simply dx vector dotted with dx vector. Now let us check what we had obtained for the expression of dx vector. So dx vector, we had this expression d capital X vector plus dx vector dot grad of u. So we'll utilize this thing. Can you please confirm if I'm audible?
Yes, sir, you are
Sir.
No, actually,
Yes, sir.
it's raining quite heavily here, so there is, the electricity is a little bit iffy. So I thought that maybe we lost the internet also. Okay. So we have this expression. Now we want to be actually, find out the simplified expression from this. Okay, this is correct, but we have to work on this thing. So what we'll do is, for this dot product, we will go on to the equivalent matrix representation. Okay, because we are comfortable working with matrices. So you understand that this is a vector, this is another vector. So this is just like A dot B. Now A dot B in the matrix representation, A dot B in the matrix representation, what will it be? This dot
A transpose into B.
A transpose into B. Okay, so this idea is what we are going to utilize immediately here. Next, you see that I have put the square bracket around this thing. It is as if just I am changing this from simple bracket to square bracket, but actually I am going from this normal vector representation to this equivalent matrix representation, which is why here I am no longer putting this dot. It is a simple matrix multiplication between these two matrices. The first one I have converted to a row matrix by this transpose, and the second one is a column matrix. Now I want to write down the equivalent matrix representations of all of these internal things. This is the equivalent matrix representation, and here for this you tell me what should be the matrix representation of this. We have discussed this in the previous class. So what I'm asking you to do is to tell me the equivalent matrix representation of this.
Sir, grad u into dx.
Yes. So grad of u matrix dx vector matrix. And let's take a quick look at the one of the previous slides where we had discussed this. You see, this is a dot grad u grad v. We had discussed all these things, and ultimately I had told you that, see, this is the thing. Dx dot grad u is equal to grad u times dx. This is exactly what we are using here. Okay, so this becomes grad u matrix dx vector. But we have to remember that over this entire thing there is a transpose. Okay, there is a transpose over this entire thing. The second one does not have a transpose, so we are good. All right. So we will put this transpose, or we'll take this transpose inside this now. What should this be? Tell me, transpose of this entire thing.
Sir, dx.
dx transpose into nebula u
Gradient transpose.
Yes, yes, yes. Good. So people who may have forgotten, what I'm doing here is this thing, that if you have two matrices multiplied like this, and you have the transpose of this entire thing, this is equal to B transpose times A transpose. Okay, you can go back and revise. Similarly, if you had inverse here, you would obtain the same thing. So AB inverse is equal to B inverse into A inverse. AB transpose, I mean whole transpose, is B transpose A transpose. Okay, so that's the thing. And now we can go forward and do a simple multiplication. So we'll simply multiply. We'll just expand it out, okay? We just have to be a little bit patient, but the good thing about this method of approach is that we don't have to take any assumptions or anything. We just, at least till this step, we can simply proceed by normal algebra kind of way. So this last term, that's a little bit big. I urge all of you to please check along with me the individual steps that I am writing. Okay, please do not rely on what I am writing. You do it for yourself and check that what I'm writing is actually correct or not. So the best way of proceeding or attending this class would be to actually take out a copy right along with me. Okay. Now you see, up to this step, no assumption, nothing. Okay, simple algebra, we have proceeded. Now, this last term you see individually here in this grad u, you will have various terms like del u, del x, del v, del y, all these kinds of things will be present. In this one also, you will have these kinds of terms, del u, del x, del v, del y, del w, del z, all these things are present. Now, when you actually multiply this out, that will be a humongous expression. If you actually multiply it out, write all the terms, I mean, I won't have enough space on my screen to write that out, but it will be there, you understand. Now, the thing that is happening here for the last term is that you will end up with terms of this form. You will end up from here with terms of this kind of del u, del x. You will have a square term, then you will have terms like del u, del x, then del v, del x. You may also have terms like del v, del y, del w, del z, all these kinds of terms. Now, they are apparently different, but they have one unique common feature. And that common feature is that they are all non-linear terms. You see, this is a derivative, this is a derivative, this is a derivative. Individually, they are all linear things, but there's a square here. Similarly, this is a first order derivative multiplied with a first order derivative. So the degree here is 2. Similarly here, this is a first order derivative, this is a first order derivative. The degree here is 2. So this last term, it will involve the quadratic terms or the nonlinear terms. Now, the entire thing that we are going to discuss will be associated with small deformations, small strains, and within that scope, these nonlinear terms are going to be extremely small. So it is something like this, that individually this del u, del x, or del v, del x, or individually any of these terms, they will be of the order of, let's say, 0.01 or even smaller. Okay, so suppose a term is like 10 to the power minus 2 or 10 to the power minus 3. You imagine the quadratic version of that or the second degree version of that. What is the second degree version of a term which is order 10 to the power minus 2 or 10 to the power minus 3? So what I'm asking is that if del u, del x is of order 10 to the power minus 3, then what is the order of del u, del x square?
So 10 to the power of minus 6.
10 to the power minus 6, as easy as that. So there is a difference of 3 orders of magnitude. Okay, so the linear term is 1000 times stronger than the nonlinear term for a 10 to the power minus 3 thing. That is why we are going to say that in the subsequent steps, we are going to neglect this term. So this entire thing is going to be approximately equal to this thing. Now, you note what is this thing? Dx vector transpose dx vector. What is
It's a
this?
modulus of dx square.
Yes. So this is basically the dot product of the dx vector with itself. And so this is just like dx vector dotted with dx vector. So this thing is nothing but dx vector absolute value square. These two terms I'm going to club together in this fashion. You please check if it looks all right. By the way, sorry, this should be capital X. And I'm going to neglect this fourth term, which is why there is this approximate sign. You please check whether from these two, from the second and third term in the previous step, I'm obtaining this one. All right. Copy this thing and go to the next page. So I'm going to write here an equal to sign, but you understand that this is equal to, the left hand side is equal to the right hand side only under the approximation that the various derivative terms, they are very small. Okay, now what we are going to say is an extremely important thing. This particular combination that you see here, the gradient of U matrix plus the gradient of U matrix transpose, we are going to assign a name to this. Okay, we are going to assign a name to this, and that particular name is going to be an extremely important one. However, before I actually write that down, I want especially the mechanical engineering students, the 20 ME students who are already doing fluid mechanics, to tell me that suppose instead of this displacement vector here, suppose I had written the velocity vector here. So suppose instead of this, suppose I had this thing. The manufacturing students need not answer this. If they know that is great, absolutely great, but I want the mechanical engineering students to answer. Suppose I had this. What is this?
Sir, deformation vector.
Almost correct, but not quite.
Sir, sorry, sir, it is the rate of deformation.
Yes. It is the rate of deformation, but it has a special name. I want to tell me that.
The strain rate.
Yes. Rate. Yes, this is the strain rate. It's not the shear rate, okay? It's the strain rate. It's not exactly the strain rate. Something is missing here. You all know this.
Half of
yes.
Half of this is strain rate.
Yeah. So half of this entire thing, that is the strain rate. So I'm just using a different symbol here. Okay, so this is the strain rate. And this is of immense importance in fluid mechanics. Now you see here, this is not the velocity vector, certainly. We are working within mechanics of solids, and this is the displacement vector. So it is almost as if you take the time derivative of this, although it is not so straightforward like that, but in a very approximate sense, in a very informal way, if we say that if you just take the time derivative of this entire thing, you will end up with the velocity gradients, and you will get the strain rate. So this thing will be, or the half of this thing, this will be the strain, not the strain rate, rather this will be the strain. But that is like actually a tensor, a second order tensor, that's the strain tensor. So similarly, this is the strain rate tensor. Furthermore, you note that what is this entire thing in terms of matrices that we have written, either this or this. So we define this thing. We define the strain tensor. Let me actually write this. The actual name for this is the infinitesimal strain tensor, or the small strain tensor. Because remember that we are working under the assumption from the previous slide that this only works if these derivative terms are very small. That is why define the infinitesimal or small strain tensor. These two tilde symbols beneath the the variable that I'm writing that represents that this is a tensor of order 2. Just a way of writing it, and we define it like this. The equivalent matrix representation, of course, is what we have just written there. So since you're all comfortable with matrices, I always try to write everything in terms of this thing. Okay, so we can use the definition symbol here also. So this is our strain rate tensor. Furthermore, you note that whether you are working with this kind of a strain rate and this or the strain tensor, what is this entire thing? This half of grad u plus grad u transpose, is it not, okay, is it not the symmetric part of the gradient of u tensor or this matrix? What I'm trying to say here is that suppose you have any matrix, okay, anything like this. This can be equivalently written as half of, again, you have learned this in your linear algebra classes. This can be written very simple to see this. I'm sure all of you have seen this thing, okay? Any matrix can be written as half of A plus A transpose plus half of A minus A transpose. So this first part, okay, this first part is referred to as the symmetric part. Why it is referred to as the symmetric part?
Sir, if we observe the elements, there will be, I mean, Aij equals to Aji.
Exactly, exactly. Or you can simply note that if you consider this part, okay, if you consider this part and you take the transpose of that, it will result in the same thing. Why? Because you can just do it in a one line. If you take the whole thing and you take the transpose of that, it will result in the same thing. So A transpose is simply A. Okay, so just the order of this thing has changed, but it is same thing because matrices are commutative. Okay, so whenever you have any matrix, and this is just like a special example, gradient of u, this matrix, it will have a symmetric part, and that symmetric part is what is referred to as the infinitesimal or the small strain tensor. This is extremely, extremely important. It is extremely important. Why? Because it gives us a connection between the various components of the strain tensor with the derivatives of the displacement. Okay, so I will not write down all the expressions. You do this for yourself. So right now, whatever we have written, this is not pertaining to any coordinate axis. But suppose we do work with Cartesian coordinate system, that is the XYZ coordinate system, then this strain tensor will be epsilon xx, epsilon xy, epsilon xz, epsilon xy, epsilon yy, epsilon yz, epsilon xz, epsilon yz, epsilon yy. This is our strain tensor. Since this is equal to that, you go ahead and try to find out in terms of, okay, so in terms of
the last element is it should be.
I could not hear you. Please tell me again.
So the last element of that matrix, epsilon yy.
Oh, sorry, this is epsilon zz. Sorry. This is epsilon zz. So you express this thing in terms of the derivatives of u v w. If you expand this out thing, this gradient of u, the symmetric part of that, you'll be able to obtain that. So what I'm asking you is that you will find that epsilon x6 is equal to half of del u del x plus del u del x, which is nothing but del u del x. Similarly, you will find that epsilon xy is equal to half of del u del y plus del v del x. Okay. So what I want you to do is obtain the rest of the things. Okay, rest of the things means expressions for epsilon xz, epsilon yz, epsilon yy, epsilon zz. Okay, and once you write them down, you will notice that there is a very nice symmetricity to it. It's like this, that whenever you have this epsilon xx, it is the displacement along the x direction with respect to the derivative of that with respect to x. When you have the subscripts as x and y, you will have the derivatives involving the del x and del y, but in the numerator, they are kind of switched. So the derivative of x is taken for the displacement component along the y direction, and the derivative with respect to y is taken for the displacement component along the x direction. So you can, even without working it out, you can almost from this symmetry, you can find out, or you can write down that epsilon yz is going to be what? Can you tell me what is going to be epsilon yz?
So del u
Sir,
del
half of
y plus del v,
Del v by
del u
del z
del z
plus
plus del v del y.
Say that again. Epsilon yz is equal to half of
del v by del z plus
del v by del z plus
del w by del y.
del w by del y. Very good. Okay. What will be epsilon zz?
So del w by del z.
Yes. And finally, what will be epsilon xz?
Del u by del z plus del w by del x.
Yes. All right. So you get the hang of it. So it's like that. Now, all this is fine, but so let me actually write that down. Okay. So I'll take this thing. I'll take this thing and I will go to the next page. Okay, so we have here this thing. Now, can I not write it like this?
Sir, it will be 2 times.
It will be 2 times. You're absolutely correct. It will be 2 times. What I want to do now is, you see this dx vector, same thing dx vector here. Can I not write the dx vector as the dx vector magnitude times the unit vector along that direction? So this dx vector will have a unit vector along its direction. I'm just taking out the magnitude and then I'm multiplying it with the unit vector, which means that the equivalent matrix representation will be simply like this. Similarly, if I have the dx vector transpose, it will be simply dx vector magnitude times the transpose of that unit vector, which means that in the next line I can write like this. From this one, I'm going to take out this thing and from this one I'm again going to take out the magnitude. So I'll end up with dx vector magnitude square times the unit vector along the dx transpose of that, this thing. Now, very quickly I can write this down, that this is dx vector magnitude square divided by d capital X vector magnitude square. So I'm dividing throughout by dx vector magnitude square. Like this. Now let us not forget that we had already defined earlier this thing. Okay, so we already have this thing. So let me go back and put it in the rough column here. So from this, do I not have this as 1 plus epsilon whole square? Please check from this step to this step, this is correct or not.
Yes, sir.
Yeah, this is correct. Simple algebra. Now what we are going to do is, this is 1 plus twice epsilon plus epsilon square. Now you see earlier we had neglected all the strain terms involving the, or all the derivative terms involving the squares. Okay, same idea applies here. We have this epsilon, it's a very small, it's going to be a very small magnitude. So this term compared to this is quite small. In fact, this epsilon itself is very small compared to 1. But the good news is that from both the left hand side and the right hand side, this 1 is cancelling out. So this 1 is cancelling out from both the left hand side and right hand side. So all that we have to neglect is this epsilon square compared to this epsilon. So neglect epsilon square compared to epsilon. So the idea is the same as before. So we end up with, again, this, after you have cancelled this neglected this epsilon square, you will end up with twice epsilon is equal to twice of this thing. So ultimately what we are going to obtain is epsilon is equal to twice n hat transpose strain tensor times n hat.
So 2 factor will not be come. I think 2 will be cancelled.
Yeah, that's a bad mistake. This 2 factor is not coming. Okay. Now please note one very important thing. What is the order of the tensor on this right hand side? Individually, this is a tensor of order 1, meaning it's a vector. This is also a tensor of order 1. This is a tensor of order 2. But overall, what is the order of the tensor here?
0.
Yes, because it is a scalar quantity. When you actually multiply this out, so this is a 1 into 3 matrix. This is a 3 into 3 matrix. This is a 3 into 1 matrix. If you do the overall calculation of this thing, you will end up with a single value, which must be true because on the left hand side it is a single value. Now, in order to avoid any confusion, I think it's a good practice to write this epsilon with a subscript n, meaning that this is the strain along a particular direction. Okay, this is the normal strain along a particular direction. But at the same time, you must never forget that this is obtained under the assumption that the derivatives of the displacement vector components with respect to the various coordinate axis variables, they are very, very small. So del u, del x, del v, del y, all these things are very, very small. So overall, only under the scope of small deformations, small strains, that this thing works. Okay, I should not say small deformation, I should only say small strains. Okay. So we have this expression, and this is the thing that we were trying to find out. And please note that this expression that we have just found out, it is equivalent to the expression for the sigma nn or the tnn that we had found in the earlier topic. And you can in fact make a comparison right hand side with that what we had obtained earlier. All right, this is about the normal strain or the strain along a particular direction. But just like we had talked about earlier in the previous topic about the stress component along the normal direction and the stress component in the shearing direction, we must also take a note that we have still not talked about any kind of shear. How can we do that? Does anyone have any idea? How can we talk about shear?
So
when we wanted to talk about the normal strain, we took a particular direction and we did some manipulations, some matrix algebra, and arrived at this expression connecting the strain along the particular direction represented by the unit vector n with the strain components referred to the XYZ coordinate system. My question is, what should I do? Like equivalent steps should I do so that I can obtain the shearing strain?
So instead of n hat, which is along the normal direction, so if we change that,
Change that to what? That is the question.
Direction of means towards the surface. Means
see,
perpendicular to normal.
Sir, if we include cross product.
See, okay, it's good that you said this thing. Okay, there is always this big confusion whenever we try to draw an analogy between the strain and the stress. Earlier, when we were talking about stresses, what we did was we took this three-dimensional body, we take a cut plane, saying that the unit outward normal to it was along a particular n hat or something, and we considered the traction vector there, and then we took the component of it along the n hat, and we said that this component is what we'll call as TNN. And that TNN expression we found out exactly like this. So far, so good. Here also, you are trying to find out the strain component along this n hat direction. This n hat now is represented by the capital N. But when I asked you about the shear strain, you immediately told me that I should similarly take a component along the surface. But please note that for this, I have not actually taken a cut plane like this. For the strain, nowhere you will see that if I go back to the previous pages, nowhere I have taken any cut plane. So there is no question arising of when you want to talk about the shear strain, there is no question of going along a surface of any plane. So something has gone wrong in your understanding. Okay, and it is good that it has gone wrong. It is supposed to go wrong, which is how you can deliberately make a correction in your thought. So you tell me what is going wrong. Somebody is saying something, but it is very feeble. Your voice is very feeble. I could not hear.
Sir, now is it audible?
Yes, yes. Tell me.
So we consider the inclination of the line between P and the another point.
Yes.
Yes, sir. Here PQ and P dash Q dash.
Right. Right. So you see, there is no question of taking any cutting plane when we are talking about strings. Rather, when we are talking about strings, we are only bothered or concerned with what is happening to elemental line segments. Just found out we were only thinking of what is happening to this straight line as it is going from this undeformed configuration to this deformed configuration under some given load. Okay, so we are only bothered about what is happening along that line, this line. So along this line, the unit vector is capital N hat. How much is it changing along that direction? That is our question. Okay, So you should not think of anything which is lying along a surface, okay, for the shearing direction. Rather, you go back to the geometrical interpretation of the shear which you had studied earlier. So what is the geometrical interpretation of the shear string?
So we consider a small point mass, and for that the angle between the two perpendicular lines, how much it is changed.
Yes, that is the important thing. So for shear, okay, so for shear, so let me just remind you that for shear, what we do is we consider two perpendicular lines like this. Okay, if you want, you can complete the square, and this is the undeformed configuration, and what you say is that the shear is defined to be such that let this square deform in this kind. So this change of angle here plus this change of angle here, these two together combined is what is going to give you the shear. So the shearing strain is always associated with two perpendicular lines. Okay, you have to take two perpendicular lines, let them rotate like this. This one is in this direction, and whatever the change in angle, mind you, shearing strain is not this angle, okay? It is not this one. Rather, it is this one plus this one. Both of them together give us the shearing strain value. Now, when we are talking about, so this is about the two-dimensional notation. It is easier to visualize these things. That is why we draw like this. But in the general three-dimensional case, how do we I mean, consider this thing in a very general way? So the plan is like this. So going forward, in order to obtain the shearing counterpart of this previous expression, this is for the normal strain. Okay, I can even write this down. Normal strain along a particular direction. For the shearing strain, what we'll do is we will not consider these perpendicular lines. We will generalize even beyond that. What we'll do is we'll consider two lines which may be at some angle theta. Okay, so let's say this is PQ and this is PR. Let the angle between them be theta. This is in the undeformed configuration within part of a larger body like this. Okay, I'm not drawing that larger body. Just imagine that these two line segments are embedded within a larger three-dimensional body. What we'll say is that under some load, this body will deform, and when this body deforms, the angle between this PQ and PR, it is going to change from theta to theta dash. So let's say in the deformed configuration, it becomes like this. So this becomes theta dash. This is now P dash, this is Q dash, this is R dash. This is theta dash. The shearing strain in general, or the idea which will lead us to the definition of the shearing strain in this general three-dimensional way, will be basically be obtained from theta minus theta dash. Okay, so this theta minus theta dash, when we obtain an expression for this, that will give us the overall idea. All right, but of course we have to do some work before we can obtain an expression for that, and you will see it's going to come out in a very neat and clean fashion. So first of all, what we'll do is we are not going to consider two lines. Rather, we have been talking about for the normal strain or regarding a particular direction. We are going to persist with that. We are going to talk about that particular direction question. Question is, what is the change in direction? What is the change in direction of an elemental line segment? This is our question. So what we are saying is this, that given an elemental line segment PQ, which is this n hat given by the n hat, in the deformed configuration, it becomes P dash Q dash. And because it is generally deforming, this n hat is no longer n hat, rather it becomes some other direction in small n hat. Question is that given n hat, find small n hat. As easy as that. Okay, the question is very clear cut. But of course, you have to understand something else must be given to us. What is that something else given to us? The something else that is given to us is the nature of the displacements that is taking place all throughout this three-dimensional body. Meaning to say that if you have the information about the displacement at various points within the body, you may as well go on to find out the strain tensor or the values of the strain components at various points within the body. So we not only know this n hat, but we also know the components of the strains at various points within the three-dimensional body. Using these two pieces of information, we can find out the n hat. So let's see how this is all coming out. So we'll go back to this expression. You know this, but let me just write it down formally so the idea will be absolutely crystal clear. This is again so this is in the deformed configuration, that is where the small n hat is. This is the capital. What should be this? This is simply dx vector n hat dot grad u. So I take this or I divide this previous equation throughout.
So your voice is breaking.
Is it better now?
Yes, sir, now it's previously it was not audible for 5-10 seconds.
Oh, okay. So we have this, we start with this thing. We arrive at this next line by just taking the dx vector magnitude, write this in terms of the unit vectors along the d capital X vector. This is simple algebraic manipulation, and we obtain this thing. Now you tell me what is this thing, and just give me a second. Let me switch on my charger for my laptop. Yeah, tell me what is this d small x vector magnitude divided by d capital X vector magnitude?
1 plus e. 1 plus.
This is simply 1 plus epsilon. Is it not? Simply 1 plus epsilon. So we obtain this thing now. I'm not changing anything on the right hand side. So the answer to the question that what is this n hat is simply this thing. If you want, you can write this with a e capital N, epsilon capital N subscript, just to be consistent with our previous notation. That's the answer. Okay, this is the answer that we are looking for. Now, by itself, this is good. It's a useful thing. But what we really want to do is to utilize this particular information, this answer that we have obtained here for the small n hat, in order to obtain this one, theta minus theta dash. So the first intermediate thing that we have done is to obtain this change in the direction of an elemental line segment. Now we are going to consider another the question which we're actually interested in, which is the change in the angle between two elemental line segments. Okay, so this is our next question. Change in the angle between two elemental line segments. So basically what we are saying is this. We have PQ and PR. This angle is theta. This is P dash, Q dash, R dash. Also note that this particular thing, we'll call it N1 hat, and this particular thing we will call as N2 hat. So PQ elemental line segment, the unit vector along it is N1 hat, and the unit vector along the PR elemental line segment is N2 hat. Correspondingly, this one will be small n1 hat. This one will be small n2 hat. And the angle between them will be theta dash. And we are interested in finding out theta minus theta dash. Okay. So given theta between n1 hat and n2 hat, find theta dash, because if you find theta dash, you can find out theta minus theta dash between small n1 hat and small n2 hat. So tell me quickly how I should proceed.
So we can consider dot product of both of them and divide by the magnitude.
Eric, that's exactly what we are going to do. Okay, so we have this thing. Okay, so this n1 hat dotted with n2 hat, that is just cos theta dash. Is it not? It is cos theta dash. Furthermore, this n1 hat or the n2 hat, because we have already done what we have done in the previous page, we can utilize this expression to write in the individual expressions for the n1 hat and the n2 hat. So what will be n1 hat? This will be 1 plus epsilon n. Let's say this is n1, or maybe I'll just write it like n1 like this. Or better to write it properly like this. Okay, nice and clear. This is n1 hat plus n1 hat this thing. Please note that I am putting the 1 over the unit vectors, but there is no 1 over this grad of u, because grad of u is common to the overall body. Okay, it is not pertaining to any particular direction. This grad of u is evaluated at a single point, and that point of interest is this point P. This PQ denotes a certain direction, this PR denotes another direction. Those individual directions are represented by this N1 and N2. That's all there is to it. Okay, so this entire thing is dotted with this. Fine. So all the actual brain work which is required is done. Rest of it is simple step-by-step algebra. Okay, so just in order to avoid writing these denominators, I will club them together and put them on the left hand side. I can even write this as cos theta dash directly. Okay, now you see I'm basically going to do the dot product of this numerator here and the dot product with this thing. So it's like this. So I'll just skip one step here. What I'll do is I'll take the matrix representation of it, transpose of that, right. So rest of what I'm going to do is something that I have already done before, except that earlier it was just the only one n hat. Now there are two different n hats, n1 hat and n2 hat. We have to be careful about that. Otherwise, whatever we have done earlier, it's going to follow exactly like that. So let me do this very quickly. So I will skip a step here. I'm sure you will be able to understand. So I'm just going to multiply this out. In fact, I can skip the step here itself. Leave it. I'll do it now. So n1 hat multiplied by this n2. This is matrix plus n1 hat transpose multiplied with n grad u.
Sir, I think it would be the reverse of that.
Which one?
Sir, in this second part of first bracket.
This one?
Yes, sir.
This one. I'm still putting the transpose outside. I'm not putting it. So in the next step, it will be n1 hat transpose grad u transpose.
Sir, initially it was of n1 dot grad u.
Yeah. So if there is no transpose, then so just like you see here, n2 hat dot grad u, that is grad u times n2 hat. So this
Okay,
is
yes,
also
sir.
like that. So there is a transpose of that. It will become n1 hat transpose then grad u.
Sir, I forgot shifting because
Yes,
of converting into
yeah.
matrix.
So okay, so where was I? have done these two things. Next, I will do this. So now I'm going to reverse this thing. So n1 hat transpose grad u transpose. This is barely visible. Okay, and I will neglect the higher order terms. Okay, because this one multiplied with this one will again result in these quadratic terms which I want to neglect. Okay, so I've done quite a bit in going from here to here, but it is good. Now you see on this left hand side also, because I'm going to neglect these higher order terms, at the same time I want to neglect the higher order terms here also. Okay, now you see this thing is what cos of theta. This is simply n1 hat dotted with n2 hat. That is simply cos theta, because this is n1 hat, this is n2 hat. The dot product between them is simply cos theta. That's this. Again, like before, I'm going to write these two things together. and I'm going to neglect this higher order terms. So this is actually going to be not equal to, rather an approximation. The left hand side also, I'm going to neglect these terms, these epsilon terms with respect to 1, because note earlier I had already told you that epsilon is very small, so epsilon square is much smaller than that, but epsilon itself is much small compared to 1. So this is going to be cos theta dash is almost equal to cos theta plus this thing. Now again, you recognize that this particular combination is nothing but the twice of the strain tensor. So I'll just copy this thing and go to the next page. And from now I'm going to write this as equal to, with the understanding that I have utilized all those simplifying assumptions. It's a very nice expression. It's especially nice because these kinds of expressions you can immediately code it up in your computer. All right. Now, what we are going to do is like this. We have obtained the change in the angle, or we have obtained the information regarding the angles, this theta dash given this theta. This can be something easily computed. But we want to go a little bit further from this, and we want to see what happens in the special case that theta is equal to pi by 2. Because remember, that is our original intention in order to go towards the definition of the shearing strain, or the expression of the shearing strain. So when theta is equal to pi by 2, what happens? This cos theta will become 0. This theta dash, cos theta dash, so it's like this. The picture has now become like this, that you had originally your P and Q like this, and your P and R like this. So this angle was theta equal to pi by 2. And now in the changed configuration, in the deformed configuration, this has become like this. P dash, Q dash, R dash. This has now become theta dash. But can we not write theta dash in terms of this original theta? Meaning that can we not imagine it's something like this, that theta dash is equal to pi by 2 minus gamma, because we know that this angle plus this angle, okay, these two angles together, this is gamma. Okay, this angle and this angle together, they are the gamma. So pi by 2 minus gamma is theta dash. So that's exactly what I'm going to write here. Cos of pi by 2 minus gamma is equal to, this is 0 plus whatever was present here. Now all the strains and everything, they are small. That is something which we have repeatedly used. So this is giving me sine of gamma, but that sine of gamma is approximately equal to gamma, and that is equal to twice of this very same thing. And this is the expression that we wanted to find out. So earlier we had obtained an expression for the epsilon n. Okay, so just to recap, earlier we had found out epsilon n is equal to n hat transpose epsilon n hat. So this was our normal strain, and this is our expression for the shear strain. There's a slight difference between the two in that in this one we have this 2 factor, and there is the presence of 2 different unit directions here, which makes sense because we are talking about the shearing strain. And for this epsilon n, there was no 2 factor, and we were only talking about a particular direction. So as far as the underlying theory of whatever you need to do in this chapter, it's done. Okay, the rest of what I'm going to do is simply doing simplifications from these 2 expressions. Okay, of course, there are many things to discuss yet. I will do that, but in terms of the hardcore basic things that we had to discuss, we have finished it. Okay, rest of it is just simplifying and breaking down these things to have a better visualization, better understanding, and to get formulas which will be useful for solving problems directly. Okay. So does anyone want to say something at this point?
So am I audible, sir?
Yes.
So actually, I want to ask one thing. So while solving the questions, epsilon n or epsilon means sine gamma,
Yeah.
we will calculate. Then it will be like we will get a magnitude, no? Means
Yes, you will get answer. Yeah.
yeah. So we have done approximation for calculating epsilon n.
Yeah.
So means we can also can you go to upper slide, sir? That
Which
1 plus epsilon to the whole square, that slide.
where we made the approximation.
Yes, sir. Yes, this slide, sir.
Yeah.
So if we directly take the square root from here, so can we not get means somehow more precise answer?
Yes, you will get more precise answer, like with more accuracy.
Because we
But-
have to ultimately calculate the.
Yeah. So let me tell you this. You will I will release the tutorial sheet today. Okay, you will see the values of the strains that we are working with. Most of the values will be in the order of 10 to the power minus 6. Okay, so it's not something that like 10 to the power minus 6 or 10 to the power minus 4 actually. Okay, because it is something like 350 times 10 to the power minus 6, something like that. Okay, so the order of those answers for the strains is usually 10 to the power minus 4. And that is not something which is just like a product of a textbook answer. It's not like that. In real practice also, these are the kinds of values which get measured. Okay, so at that, so I told you like what happens when you have this, when you neglect terms of 10 to the power minus 6 compared to 10 to the power minus 3. Imagine when the strain itself is order 10 to the power minus 4. So there is 4 orders of magnitude of difference between the linear term and the quadratic term. Because you are then comparing 10 to the power minus 4 with 10 to the power minus 8. You can do these things, but like an engineer's job is to make life easier for all humanity, but first of all to make life easier for himself also. Not at the cost of doing a botched work, but as long as it is all right and valid and makes sense, please do the simplifications. Don't unnecessarily, for the sake of doing calculations, do calculations.
Okay, sir.
Okay, you can do the calculations like that. Okay, but it will not give you any benefit. All right.
Yes, sir.
It's a good question. I mean, one can always answer. I mean, one can always question, since we have these exact expressions, why bother going through all this trouble of doing this simplifications? All right. So next, what we are going to do is exactly something analogous to what we did in the topic of stresses. So in the topic of stress also, topic of transformation of stress, we first of all obtained the general 3-dimensional expressions for the sigma nn, and then we specialized to the 2-dimensional version by considering the special case of a plane stress. We considered plane stress, a plate-like structure which was under a certain kind of loading, and we said that this is a very common engineering situation, and this gives rise to plane stress, where sigma zz equal to 0, tau zy equal to 0, and tau xz equal to 0. In a very similar manner, now in this topic of transformation of strain, we are going to consider something analogous, which is referred to as plane strain. What is that plane strain business? So simplifications. Under the consideration of plane strain. So first of all, let us try to understand what this plane strain is. You see, earlier when we were talking about plane stress, we talked about a flat plate like this, which had a very small thickness like this. Now what we are going to consider is you consider a beam of general cross section, some general cross section. Okay, long beam like this. Something like that. Okay, it's a prismatic cross section. And imagine that the loads on it are distributed uniformly. This is very important to understand. The loads on it are distributed uniformly, and not just uniformly, they are acting in such a way that if you consider this to be your x-axis, this to be your y-axis, or maybe it will be better if I consider it like this. Let's say that this is our x-axis, this is our y-axis, and this is our z-axis. If we set up our coordinate axis like this, then these loadings, they are not only uniform, but they are applied in such a manner that they do not have any z component contribution. Okay, meaning that they will not have any inclination like this. They will not be inclined like this. Okay, that is not going to happen. If they have something like that, it means that they certainly have a component in the x direction, but they also have a component along the z direction. That is not allowed. Okay, so these things are going to be perfectly parallel to this xy plane, these loadings. Okay, this is absolutely very important. Furthermore, none of these loadings will have any dependence on the z, meaning that they are constant values along this z. Under these conditions, what is going to happen is that there will be no difference in the nature of the deformations that are taking place at a cross section here, or at a cross section here, or at a cross section here. No matter which cross section along the length or along the z direction you pick up, they are all going to look identical. In terms of the deformation, they are all going to look identical as long as those conditions are fulfilled. Okay, now from this you tell me if you have any confusion. So this seems like a rather arbitrary kind of thing, very restrictive in nature, but believe it or not, in real engineering practice, this plane strain business, it is actually very much applicable in a lot of professional engineering situations, which is why we make such a fuss of teaching you plane stress and plane strain. Okay, both of these, despite looking so restrictive in their assumptions, are widely applicable. Okay, nevertheless, you tell me if you have any confusion. It's absolutely important to have no doubt about this thing.
So here the cross section area is constant throughout the z-axis, or
yes, they are.
Means if it is not, then we cannot use plane strain.
Then you cannot directly say that it is under plane strain. Okay, it may so happen coincidentally that the nature of the deformations along a particular z direction at a particular xy will be same, but overall you cannot directly say that even if the loadings do not have any z component contribution, even then you may not be able to say that the deformations are going to be similar.
Sir, the loadings will be same throughout the length.
Yes. It has to be a uniformly distributed load. Like in beams, in the beam problems, you have taken examples like this, right? You have a beam like this, and you have a uniformly distributed load like this. That is the kind of example that we're talking about.
Can you give one example in real life? So means how
I just gave you like this. So you can consider this beam to be part of a roof structure. Okay, so suppose you have a roof, or I mean, this can be the roof of a particular floor or the ceiling of a particular floor, or the floor of a particular floor of a particular story. And these beams, they will be supported by these kinds of beams running parallel to some direction. Okay, so because of the load from this floor on this beam, so this beam is like this, okay. Because of the load from this, the distribution of load on this beam is going to be more or less uniform. Okay, so in that kind of a situation, it is under plane strain. And please don't think that one or two people standing on the floor is going to make a humongous difference to it. It is only going to make a few percentage difference to the loading on this beam. Okay, it hardly matters. 1 or 2% standing there, or even for that matter 10% standing there, they have negligible weight compared to the weight of the actual floor. All right, so let's try to see what happens under this kind of a situation. You understand that on any particular cross section, the deformations will be such, okay, the deformations will be such that u will be a function of only x and y, the v will be a function of only x and y. What will eventually happen from all of these things is that under the plane strain conditions, okay, under the plane strain conditions, this is the most important thing which you must remember. Epsilon zz is equal to 0, epsilon zx is equal to 0, and epsilon zz is yz is equal to 0. So the strain tensor that we had talked about earlier referred to a Cartesian coordinate system or the xyz coordinate system. It is going to look like this. Remember what happened in the case of plane stress? This is exactly the same situation. So effectively, our whole game is taking place over these first two rows and first two columns. All right. Now, with this understanding, we want to go back to our previous expressions, the expressions that we had obtained previously for our epsilon, this one, epsilon n. This epsilon n and this gamma, and see what we can obtain. Okay, so we'll quickly try to go through this. Epsilon n is equal to n hat epsilon tensor n hat. There's a transpose here. So what we want to specify in this 2 dimensions, so remember now because we have mentioned that we are only going to be bordered with this x and y direction, we only need to focus on our xy plane, whatever is happening in that xy plane. Okay, so suppose you take your unit vector, this unit vector like this. This is our unit vector, let's say. And let's say this angle is theta. So the components of this n hat, it's going to be cos theta, sin theta. This is the matrix, explicit matrix representation, which means that epsilon n, this is going to be what? Cos theta, sin theta, epsilon xx, epsilon xy, epsilon xy, epsilon yy, and then again cos theta, sin theta. And if you do this, the result that you will obtain will be exactly the same that we had obtained earlier for the sigma nn. Okay, in an analogous situation, whatever we had obtained for the sigma nn, the exact same expression will obtain for the epsilon n. So all of you do this quickly. I'll give you 15 seconds or something like that. Do the expression and tell me what you are getting.
Sir, epsilon xx into cos square theta.
So I want to write down directly in terms of cos 2 theta and sin 2 theta. Okay, you check whether you are getting that. So it's something like this. And please note, whatever I'm doing, it is exactly identical except for this epsilon symbol to what I was doing earlier for the sigma. You please check. Okay, I'm writing down this final answer in terms of the cos 2 theta and the sin 2 theta. So this is the thing. Now please note that we have taken this along this arbitrary direction n hat, but we may as well say that this is our x dash. Just like we had said earlier, so this epsilon n, we may say that this is nothing but epsilon x dash, just like we had said earlier for our sigma x dash, x dash. Tell me quickly now, what should be epsilon y dash, y dash? If this is x dash direction, the y dash must be along this one, 90 degrees to that. This must be y dash. From this one, you tell me what should be epsilon y dash, y dash. Don't do any derivation. Directly from this, you tell me. All that I have to do is replace theta by theta plus 90 degree.
Yes.
Yeah, tell me. So this will be cos of twice of 90 plus theta. So basically cos of 180 plus twice theta. That is minus or plus?
Minus, sir.
Minus.
Minus.
Yeah, good. So what I'm doing here is this theta goes to theta plus 90 degrees. And what about this thing?
It will also be negative.
Okay, so these are the things which you will actually find in Beer and Johnson, where they have done the derivation by taking some kind of geometry and arguing about this and that. But I think what I have presented here is far more systematic, and it actually prepares you for what you are going to study later on. Next, our job is not yet done because we have to go to the expression for the gamma also. Okay, and I want to look at what happens for this gamma x dash y dash. So let's go to the next page, and our expression for gamma was twice of this thing. I'm just repeating the expression here. And if I just borrow this diagram, you note that n1 hat, that will be just like before, cos theta, sin theta. What will be n2 hat? So n2 hat will be along this y dash direction. What will be n2 hat?
So minus sin theta,
Minus
Very
sin
good.
theta.
Yeah,
cos theta.
very good. So basically what we are doing is replacing this thing here by cos of theta plus 90 degree and this one by sine of theta plus 90 degree. Correct. And then you just do the calculation.
Sir, I'm not getting why N2 direction is along y dash.
You look back at this derivation. Look back at this derivation. So here we were initially taking this to be just some angle theta or phi or whatever. Okay. And then at the end, what we have done for this gamma, when we wanted to obtain gamma, we took this theta is equal to pi by 2. You see here, this was PQ and this is PR. The angle between them is pi by 2. Okay. So we are trying to obtain the shearing strain associated with these two mutually perpendicular lines. So this formula, it pertains or it is concerning this situation where you have two mutually perpendicular lines. Now, when we are doing this problem, you see this one direction we have taken along x dash. In order to use that formula, we must take another line segment or another direction which is perpendicular to it. The one perpendicular to it is this y dash. Okay, so this angle here is 90 degrees. So since x dash referred to the x direction, the original x direction is theta, this one should be theta plus 90 degrees. That's right.
So N1 and N is same.
Which one?
N1 and normal N.
Yes. So you see, because I am interested in gamma x dash y dash, so this x dash should be the same x dash that we were talking about earlier. This is the same x dash we were talking about. Okay, so the normal strain along this x dash direction is this, and the shearing strain associated with this x dash and y dash is what we are going to derive now. So do this and tell me what you are getting. Try to tell me in terms of the twice theta. If I were in your place, I would just go back to my notes from the stress topic and tell my professor the expression from that replacing sigma by epsilon. So the answer will be like this. Again, the exact same thing we were obtaining for that case, where you are replacing the sigma xx by epsilon xx, sigma yy by epsilon yy, and the tau xy by this epsilon xy. Please note that in Baer and Johnson, they have not exactly given this expression, rather they have replaced this epsilon xy by gamma xy. Okay, and note that gamma xy is equal to twice of epsilon xy. Okay, so there is a thing like a half of gamma xy in the book. But I find this is just easier to remember because it is exactly like the stress formulas. So that's it. We have finished this thing. Okay.
Like,
now,
sir,
yeah.
sir, here x dash y dash is our initial condition, and we are We are applying stress in the direction of xy. That's
We are
like
not
our
applying any
initial.
stress. We are not applying any stress. There is no question of any stress here.
Sorry, sir. Sir, here our initial condition is x dash y dash or xy.
Our initial is x dash y dash.
Okay, sir. Okay.
Yeah, but the information that is available to us regarding the strains at this point, that is available to us with referring to the xy coordinate axis. So this question is very, very important. Everyone listen carefully. It is not that we are trying to obtain the change in the angle between two line segments which are lying along x and y. It is not that. Rather, what is the role of the xy here? The role of the x and y is to give to us the information regarding the displacement field. Because if we know the displacement field, we can do the various derivations with respect to x and y and obtain the different components of this epsilon xx, epsilon xy, all these things. This is the information we are obtaining with referring to the x and y. That is the only role. However, when it comes to the shearing strain, we are not referring to two perpendicular lines which are lying along x and y. That is not the thing. Rather, the two perpendicular lines are lying along this x dash direction and the y dash direction. So earlier in our derivation, whatever we had written for this PQ and PR, that PQ and PR are lying along this x. So you can imagine that this is PQ and this is PR. So after that, after the deformation, what is going to happen is that this is going to become like this and this is going to become like this. That is what we are obtaining through this gamma x dash y dash. Okay, so please be absolutely clear with that. So I'll give you another minute, maybe a few more seconds to just think if you have any doubt regarding this thing. I know many people, so it's much easier to understand the stress because we just have to deal with one plane and maybe the unit outward normal to it. But here things are a little bit more sophisticated. Okay, you think about it. I'm sure when you, sit down peacefully and study for yourself and introspect a little bit, some more doubts will come to your mind and we can clarify them as we go along. Let me try to cover another subtopic now. And the sequence that we are going to follow is exactly like before. Earlier we had talked about principal stresses after we had finished this up. Similarly, here we are going to talk about principal strains. So we had defined principal stresses to be the normal stresses on those planes where the shearing components of the tractions are zero. That was our definition. Okay, we took those planes to be the principal planes on which the traction vectors are oriented exactly along the unit outward normal only, such that the shearing components of the tractions are zero. But here we are not taking any plane. There is no cutting plane. There is no such thing like that. So what are we going to say? What is the physical motivating question which will allow us to step into principal strains? So it's very simple actually. Okay, all that we have to ask ourselves is that we are at a certain point P and we have this XY coordinate system referred to which we have the various components of the string. And as you have seen that if you want to look at any other direction, let's say X dash or Y dash, you can obtain the stress component or the strain components referred to those directions, just like we have done. Okay, we have obtained the X dash, the Y dash components of the strains. It is very much possible. We have also managed to find out the shearing strains. Question is there or do we have certain directions along which the normal strains will be the extreme values? If we have such a thing, those directions will be referred to as the principal directions, and the values of the normal strains along those directions are what will be referred to as the principal strains. I repeat, in our search of the values for various kinds of strains along various possible choices of this x dash, do we perhaps arrive at such a situation where from all of these choices we arrive at such a x dash where the value of the epsilon x dash or the value of the epsilon y dash is an extremum. Extremum means it can either be a maximum or a minimum of all the values. Of course, you can arrive at such a thing. Okay, you have a certain distribution of strain values at various thetas. You can of course arrive at maximum and minimum values. Okay, so those maximum and minimum values together, they are the extremum values, and those extremum values are the principal strains. That's all there is to it. This is the easy definition. But how do you obtain the values? Well, one thing you can do is, like, there are different ways of doing it. One thing is you can do this, you can try to do a d epsilon x dash d theta. This you can do. Equivalently, you can do a d epsilon y dash d theta also. You'll get the same thing. Or you can try to do another thing. You can try to set this gamma x dash y dash to be equal to 0. You'll get the same thing. Or you can take a very general notion of this thing and maybe even go back to the three-dimensional version and obtain a general eigenvalue like problem, like we had done in the case of the stresses. Okay, so you have different routes of arriving at it. Now, in the tutorial sheet, I have provided you a question where you will be able to do this kind of a derivation. Okay, a clean cut, nice derivation you will be able to do. So let me not repeat that right now. Rather, what I will tell you, or rather what I will ask you, I will not tell you. Okay, again, drawing an analogy between the stresses and the strains, tell me the expressions for the principal strains for this two-dimensional version only. No need to go to the three-dimensional. For this two-dimensional version, looking at these expressions for the epsilon x dash, epsilon y dash, and gamma x dash y dash, tell me the values of the principal strains.
Sir, epsilon xx plus epsilon yy by 2.
Epsilon xx plus epsilon yy by 2.
Plus or minus. Square root of epsilon xx minus epsilon yy whole square.
By 2 whole square.
Yes.
Plus epsilon xy square. Okay, so again, so I have shamelessly lifted this from principal stress formulae. Okay, shamelessly I have copied this thing. That's all there is to it. Okay, so epsilon P1 and epsilon P2, the principal strains epsilon P1 and epsilon P2 are these things. And you can actually do, you can keep on drawing analogies between the two things. What I mean to say is that earlier, what we had done in the case of stresses was that after obtaining these two things, as well as this, the gamma expressions, we had written down, and we had written them down in such a fashion that we were able to draw something called the Mohr circle for stress. Okay, in exactly the same way, we can draw the Mohr circle for strain also. Okay, I'm not doing that because it is just like a mindless repetition of the whole thing. Okay, so just like I had done earlier, I can go on to draw a circle like this. Where, this is epsilon, this is gamma. Please note that this is gamma, okay? This is not epsilon xy, this is gamma. This here is the epsilon P1. This is the epsilon P2. This is the epsilon average, where epsilon average is equal to epsilon XX plus epsilon YY by 2, and the radius of this circle is just this thing. Okay, so this is the radius, and everything that we have talked about earlier, it follows through. Okay, even the three-dimensional version of the Moore strain, it follows through exactly the same fashion. Now that's fine, that is important, but what I personally believe is far more important is to have and is to spend some time not going through these kinds of repetitive formula and spending like too much time doing problems from strain which are exact repetitions of the stress kind of things. Rather, it is far more important to spend some time thinking about the kind of questions which was earlier asked. Like when we are talking about this gamma, we are actually talking about this new direction, this x dash y dash, and it is with respect to that x dash y dash that we are counting the change in the angle. Okay, and in order to do that, we are obtaining information from the strain values which are referred to this x and y axis. Similar is the case for the normal strain. We are obtaining the normal strain along this x direction, but the way that we are doing it is by utilizing the information regarding the strain components which are referred to this x direction and this y direction. Okay, so it seems like within the context of class, it seems rather obvious and straightforward, but unless you actively, like proactively think about it for yourself and have a very clear-cut, crystal clear understanding of these things, later on in the context of a more difficult problem where these are the fundamental things, you will be at a loss. Let me tell you this. Okay, so please do spend some like quiet time in your home thinking about these things. Okay, and try to see that even though the formula may be same for the stresses and the strains, but the fundamental geometrical basis of them are completely different. One has to, the stress has to do with the cutting planes and the concept of traction. This one has to do with the change in the line segment magnitude and the line segment direction within a three-dimensional body, or equivalently a two-dimensional body. Okay, so there is only one last topic left, and that is the topic of strain rosette. Now, it is my understanding that within in the context of mechanics of solids laboratory, you are already studying strain rosette, is it not? I asked Professor Archana Arvind because she's one of your teachers in the lab. Professor Mehir Sarangi and Professor Archana Arvind are taking your lab, right?
Yes, sir.
Yeah, so it's not a very emphatic yes. Anything wrong? Deathly silence. So has strain rosette been covered or not till now? I'm talking about this topic. Okay, let me write this down. Maybe my pronunciation is not clear. I'm talking about this strain rosette. This one.
No, sir.
It has not been covered. Yes or no? I can't hear you.
No, sir.
Okay, so it will be covered. Don't worry about it. So it's like this. Suppose you have a body, okay, some general body, and let's say you have some kind of a machine part which is shaped like this, or maybe something like this. Some support kind of thing is there. Some bracket kind of thing. Okay, and maybe there are some screws here. And you want to find out, so this is part of a larger structure, and you want to find out the strain at this particular point. Okay, what do you do? Well, like in reality, what do you do? Don't tell me about linear algebra and stuff here. Okay, what can you do? You can draw a line here. Okay, suppose you are interested in finding out the strain along this oblique direction. You can draw a line here, mark out 2 points here, position a camera somewhere here, and track the change in the length of this thing as it deforms. That is one method. But if you do that, you will be able to find out definitely the strain in this particular direction. But from that information, you will have no other way of obtaining the strains in any other direction. If you want to do that, you will have to again do repeat the experiment again, draw a line along that direction, mark out 2 points, again position your camera, spend some time and do that. Again, if you want to find out the strain along this direction, you have to again do the whole thing. And if you keep on doing this thing, you will obtain normal strains along various directions, but you will be in no position to find out the shearing strains, because for shearing strains, you need to find out the change in the angle between two mutually perpendicular lines. So what do you do? What is the way out? So there is a clever trick which people use. What they do is they have built up a special device called a strain rosette. Now, a strain rosette is a fancy name. It's just a combination of 3 strain gauges. Okay, so 3 or 4 strain gauges. Okay, so a combination of strain gauges. Are you familiar with strain gauges?
Somewhat.
Yes or no?
Yes, sir.
Yes, sir.
I think now we are going into a territory where the yes and no is going to depend on which board you had studied your +2 from. So basically a strain gauge is a thin wire. Okay, a thin wire like this. There is a coil so that you have a certain dimension of it, and like this. Okay, now do you remember from high school physics, and I'm sure no matter which board you are from, you will know this relationship that the resistance of a wire, it depends on its length. What is the relationship? In terms of the resistivity of the material, the length and the area, do you remember?
Sir, R is equal to rho L by A.
Rho L by A.
Very good. Now the JE training kicks in. So resistance is equal to rho L by A. Is it not?
Yes, sir.
Okay. So rho is the resistivity, L is the length of the wire, A is the cross-sectional area of the wire. Fine. Now, if you place such a wire on a body which is deforming, then what can happen is that as the body deforms, the wire deforms along with it. Okay. Now, when the wire starts to deform, its length and area change. When it changes, the resistance also changes. Now, if you put this kind of a strain gauge, so this is a strain gauge, okay. Of course, it is not put like a wire hanging in air like this. It is put under a nice packaging like this. Okay, very flat kind of structure, almost like a band-aid. Okay, like a band-aid, you can put it on any machine part or anything. So these two ends, they can be connected to an electrical circuit. Not any kind of electrical circuit, rather they can be made part of a Wheatstone bridge, which you are familiar with from your electrical technology studies and maybe even from your high school physics. So when this is done, then this change in resistance can actually be calibrated and it can be measured. And through that change in the resistance, the change in the length, that can be back calculated. So you don't have to keep on doing these kind of calculations repeatedly. Rather, there are devices and electrical circuits and readouts where you just have to stick this in, connect it properly, and automatically you will get the reading regarding the strain. Okay, this is a very nice device. So you'll automatically obtain the information regarding the strain. But this is along a particular direction only. So what is done is that, so this is equivalent to making those two marks, okay, that I had told you earlier. Instead of an optical device, you are using an electrical kind of device to measure the normal strain along a particular direction. But despite the apparent sophistication of this technology, you are still limited to determining the strain only along a particular direction. In order to obtain at the same time the comprehensive information about the state of strain, we consider a combination of strain gauges. And I will discuss the rest of that concept and the idea behind it in tomorrow's class. Thank you very much. Please go to your next class.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Excuse me, sir. Sir, in the expression for the gamma x dash y dash, I guess we have missed out one factor 2.
Is it? Let me check. Where is it?
So gamma x.
Yeah. This one. There must be a 2 here. You are right. All right. Thank you.
Thank you, sir.
Sir,
Yes.
also in principal stresses,
Yes.
there was physical interpretation where only there will be a normal stress, only a traction vector, all that is shear along the cross section is 0.
The shear along the cutting plane is 0. Yes.
Yes. Sir, in principal strain, what is the physical interpretation like?
I told you, no? So the principal strain is basically, it is also true that when you have when the normal strain is equal to the principal strain, the value of the shear strain is going to be equal to 0. But that is not part of the definition. The definition is like this, that where you have the maximum value of the principal strain, there it is where you have the maximum value of the normal strain, that is what is referred to as the principal strain. And that is the physical interpretation. Okay, so the maximum values or the extremum values that the normal strains can gain, they are the principal strains.
Okay, sir.
Okay.